All right, this is the View Calculus class. We're doing topic 6. For real this time, I accidentally wrote topic 6 when I meant topic 5 on the last ones. Mea culpa, which is my bad in Latin. So topic 6 is the quotient rule. So let's say that you have two functions, h and l, both functions of x. So the derivative with respect to x of h over l, right, the quotient h on top of l, where they're both functions of x, is low, d high, right, so we used L for low, minus high, d low, draw the line, square the low, okay? That's the quotient rule. Notice that h stands for high, meaning the top function, and L stands for low, meaning the bottom function. You could also see it with n for the top and d for the bottom, like numerator and denominator, but that gets a little messy because of all the d's, like dl, dh, d, whatever, yeah. So anyway, low d high minus high d low, draw the line, square the low. Notice that this is not commutative, right? Both because of the subtraction and because the bottom is just an L squared. So we're going to go ahead and walk through some examples of doing the quotient rule. So example 1, f of x equals x to the fourth over a 3x plus 1. Okay, so my high function is the x to the fourth, my low function is the 3x plus 1, right? So f prime of x is going to be low, so I write the low function exactly as it is. D high would be a 4x to the third minus high, which is x to the fourth. D low is just going to be a 3. Draw the line and square the low, so 3x plus 1 quantity squared. You're usually going to leave that denominator squared. It's just easier. But we should clean up the top. So when I distribute this 4x cubed, I'm going to get a 12x to the fourth plus a 4x cubed minus a 3x to the fourth all over this 3x plus 1 quantity squared. So we're probably going to leave it as a 9x to the fourth plus a 4x cubed all over this 3x plus 1 quantity squared. So there's my f prime, okay? So again, you can't miss a quotient rule because it has a quotient. It has division that can't be simplified. Now, if this denominator had been a monomial, like if I had flipped this in reverse, then as we saw in previous examples, if the denominator had been the x to the fourth and the numerator had been the 3x plus 1, you could actually simplify that. But you can't simplify this. And honestly, I don't suggest that you necessarily would want to. All right, let's walk through example 2. So in topic 5, which I accidentally called topic 6, I taught you some trig derivatives, right? So one of the ones that I taught you was the derivative of tangent. So I want you to derive f of x equals sine x over cosine of x. Now, it's worth noting that that is actually the same as saying tangent x. So we're going to find f prime, but what this is actually going to let us do using the quotient rule is prove why the derivative of tangent is what it is. So let's go ahead and find our f prime of x. So low d high is going to be cosine minus high, which is sine of x. D low will be a negative sine of x. Draw the line, square the low. So cosine of x, quantity squared. So the numerator is going to end up being cosine squared x plus sine squared x, which if you recall from when we did trig stuff last year in pre-calc, is actually a trig identity that you want to know, which is that sine squared plus cosine squared is 1. So I'm going to get 1 over cosine squared of x. Well, that is the same as a secant squared. So you may recall in the topic 5 video that I said the derivative of tangent was secant squared, and there you have it. These functions, sine over cosine, are the same as tangent when you write it that way, right? So sine over cosine is tangent. The derivative of tangent is secant squared. All right, let's go ahead and do example 3. All right, example 3. F of x equals 6x over x squared plus 5. Okay, so there's my high function and there's my low function, right? So my f prime of x is going to be low, so x squared plus 5 in parentheses. D high will just be a 6, minus high, which is 6x. D low is a 2x. Draw the line, square the low, so x squared plus 5 quantity squared. When I clean this up, I get that f prime of x is, this is a 6x squared plus 30 minus a 12x squared, right? So this would have been 6x squared plus 30 minus 12x squared. So I'm going to write that as a negative 6x squared plus 30 all over this x squared plus 5 quantity squared. The reason I'm leaving the denominator the way it is because that denominator is factored, and factored things are generally better. This is not factored because of the addition and subtraction in the middle, like all the ones we've seen have had this minus in the middle. They're not factored, but the denominator is. All right, very last one. We're going to do example 4, and then you're going to do a couple practice problems. I think it's 4 practice problems. All right. So example 4, f of x equals root x, so that's my high function, on top of 2x plus 3, which is my low function. All right, so my f prime of x is going to be low, which is 2x plus 3. D high, right? So d high is a little tricky because remember that this high function is an x to the 1/2, right? So the derivative of that is going to be 1/2 x to the negative 1/2, which we're going to have to deal with in a sec, minus high, which is just that root x, d low, which is a 2. Draw the line, square the low, 2x plus 3 quantity squared. So this is a little bit ugly. So it's up to you. You could try to clean this up a little bit. You could choose not to. It's up to you. So one way to deal with this is to flip this guy to the bottom, right? And that's fine, but it's going to get a little bit ugly. Another way to deal with it is just distribute this power in here. So if I distribute, I'm going to get that this 1/2 times the 2 is a 1, and this is an x to the first minus the 1/2, so it's going to be x to the 1/2. So I get x to the 1/2 plus 3/2 x to the negative 1/2 minus a 2x to the 1/2 all over 2x plus 3 quantity squared, right? These are like terms, so if you wanted, you could make this a negative x to the 1/2 plus a 3/2 x to the negative 1/2 all over a 2x plus 3 quantity squared, right? And that's fine. I will show you another. So this answer is right. Technically, so were all of these answers. If you wanted to clean this up a little bit, it's not the prettiest thing in the world, but you could. So if you wanted to clean this up, right, so we'll just take that answer and clean it up, and this is our last example. And you don't really have to clean it up, but if you wanted to, you could. So if we take this answer, I could rewrite this f prime as a negative square root of x plus a 3 over 2 root x, because that was to the negative 1/2, all over this denominator that I really don't want to mess with, right? I could get a common denominator here if I want, right? This guy's actually over 1, so I could times by 2 root x over 2 root x. It's not super pretty, but you could, right? If you wanted, you could times by 2 root x over 2 root x to get the same denominator. If you did that, you'd get negative 2x plus 3 over 2 root x, all divided by this thing, which is technically over 1. So you could get negative 2x plus 3 over this 2 root x times this 1 over a 2x plus 3 quantity squared. And so I guess the best that you could technically make this would be to have a negative 2x plus 3 over 2 root x times this 2x plus 3 quantity squared. That's probably the nicest it gets. Again, this one doesn't get super nice. The goal was definitely not to give you something that would simplify in a really fancy way. It was more just to give you something that would demonstrate how the quotient rule works. So you're going to try examples 1 through 4 now, or practice problems 1 through 4 rather.